All right, today we're going to start talking about evaluating limits without having to create a chart for every single limit that we're trying to find. So we're going to look at functions. As long as a function is continuous, meaning there's no hole or break in the graph, we can use direct substitution to find the limit. Some basic definitions here. So basically a limit of a constant is a constant itself. So that makes sense. If I have f of x equal to 2, it's just a horizontal line at 2. So obviously as x is approaching some b that we have from both the left and the right, it's going to be the value for y is going to be that line. In the same way, the limit of a straight linear function like f of x equal to x or anything like that, we just plug c in, and it's going to be c itself. And the same thing for an equation like so. We'll plug c in. So you take c to the nth power, whatever power we have, it's going to be a positive. I believe in our definition, let n be a positive integer. So be say n would be 2, so it'd be x squared or x cubed, anything like that. Okay. A few examples from the above definitions. The limit as x approaches 2 of 3. Well, it's just if you think about the graph, it's just a straight line at 3, so it's just 3. The limit as x approaches -4, we go ahead and plug -4 in. We're going to get -4 is our limit. And the limit as x approaches 2 of x squared, plug 2 in, square it, and you get 4. Since those are continuous functions, we can use direct substitution. And as I noticed, they're all continuous functions. Properties of limits. If we have a limit, what this definition is here, if we have, say, something's a scalar is multiplied by everything, we can pull that number out, find the limit, and then just multiply it at the end. So you can find the limit of the function, then just at the end multiply it limit by that multiple that we had earlier. Sum or differences means like if I have like an x plus 2x, I can find the limit of x as it approaches some number and add the limit as x approaches 2x, or whatever we're trying to find, so or limit of 2x is whatever we're trying to find. Let's say we're trying to go to x approaches 2 and x approaches 2, because it's going to be the same. So they want to know the limit as x approaches 2 of this right here. We can break that down and find the limit, each individual limit, and add at the end. We can go ahead and substitute the limit as x approaches 2 of x is 2. The limit as x approaches 2 of 2x is 4. We get 6 for our limit. That's what the sum and difference is. Same thing for the products. We just multiply the two limits of the two functions. Same thing for the quotient. Divide the two limits of the two functions, as long as the limit of this function, of the bottom function, is not 0. And for a power, anything, we just take it. If we have a function to a power, we find the limit of the function and we take it to that power as well. So here's some examples. Here's an example of that. The limit of 4x squared plus 3 as x approaches 2. So we break this down into the limit of 4x squared plus the limit of 3 as x approaches 2. As x approaches 2. We can break this one down a little farther. We can pull our scalar out of 4. So it's 4 times the limit of x squared plus the limit as x approaches 2 of 3. As x approaches 2 over here as well. We go ahead and we plug 2 in. We get 4. 4 times 4 is 6. So I was just plugging this in. 2 squared is 4. 4 times 4 is 16. Plus 3. So our limit is 19 in this case. Here. Polynomial rational number, like we said above. We just plug in. We find the limit of the top one. And we divide it by the limit of the bottom one. The limit of the top one we can break down to the limit of x squared plus the limit of x plus the limit of 2. And the bottom one we can break down into the limit of x plus the limit of 1. Sorry, I got lazy there. They all underneath all the limits, it should be as x approaches 1. What we can do and what we've learned above is we can go ahead and we can plug 1 in for each of these and get our limit since they're continuous functions. So we'll have 1 plus 1 plus 2 on the top, all over 1 plus 1 on the bottom. So it looks like I have 4 over 2, which equals 2. Okay. Hopefully we're all good with that so far. The limit of involving a radical, as long as that radical is positive, and an odd. If it's an odd, any number for C, any limit for C works. Think about this for a second. If n is an even, so like say we had the square root of C or the fourth root of C or something like that, we know that if we take the square root or the fourth root or any even root of a negative number, we get an imaginary number. So this C has to be positive if we're dealing with even radicals. Okay. Again, we just plug it in, and she works. So we're going to take, again, we plug in 0 in for x down here. So we get 0 squared times 2 is 0 minus 10. We take the cube root of that, so we have the cube root of 10, right? Excuse me, the cube root of negative 10. Cube root of negative 10. Okay, getting to the last parts here. The limit of trig functions, again, we just plug them in for every single one. So the limit of a sine function is going to be C at that limit of the sine function. We're just going to plug them in all of them and find the value of the sine or the cosine or the tangent or the cotangent of all these. Okay, so the limits of trig functions are pretty easy. All right. So I have an example right here for you. So the limit of tangent of x, go ahead and we plug 0 in for the tangent of x. So we want to know what the tangent of 0 is. 0, keep in mind these are in radians. If you like, you want to know the tangent of 0. If you remember our unit circle, 0 lies right here. Just say we have no opposite side, but we have an adjacent side of 1. So tangent of 0 is going to be 0 over 1, which is 0. All right. How about the limit of x times cosine of x? So we're going to have, we can break this down. Remember what we said above. We can find the limit of each of these separately and then multiply the limits at the end. So I'll have the limit of x as x approaches pi. And now the limit cosine of x as x approaches pi. So here I'll get just pi times, I need to figure out the cosine of pi. If you remember the cosine, it starts on, it goes 1, 0, -1, right? So -1. So the limit of this is those two multiplied together, so it'll be negative pi. And the last one here, sine squared, if you remember from our trig and pre-calculus, when it's written like that, it really means like so. What we learned above is we can find the limit of the inside function, then square it later. Square it after we find the limit. So we're going to go in and we're going to plug 0 in for x, so we need to find the sine of 0. Remember the sine graph. Remember the sine graph, it starts at 0, works its way up to 1. So we know the sine of 0 is 0, so we have 0 squared. 0 squared is obviously 0. So the limit as x approaches 0 of sine squared of x is 0. And that is it. We'll see you next time.